So in this video, I want to do a quick review of ionic compound formulas, ion charges, that kind of thing. I'm not going to be doing nomenclature in this video. So in this figure here, you can see the most common monoatomic ions. So the metals, where you have your cations with a positive charge, and then your nonmetals have the anions with a negative charge. Now, there's also another group of ions called the polyatomic ions, and you can see them here. Most common ones are in bold. And one thing to know about these polyatomic ions is that they are essentially molecular compounds that happen to carry a charge, typically a negative charge. There's one here with a positive charge, ammonium. So that means, like, for example, let's just take nitrate and sort of break it down a little bit. These four atoms are held together with covalent bonds, and then overall they are carrying a single negative charge. And let's just compare that with nitrogen and oxygen as monoatomics. Okay, so these ideas, NO3 with a negative charge, nitride with a negative 3 charge, oxide with a negative 2 charge. These are three completely different things, okay? Nitride, oxide, these are monoatomic ions that are carrying these charges. And then nitrate, again, it's basically, you could draw a Lewis structure for nitrate. One common Lewis structure might look like this. And then one way to show the overall charge would be with brackets. You can also show individual formal charges. I'm not doing that here. So again, one thing to keep in mind is that polyatomics and monoatomic ions are just completely different things. Like nitrate here is not composed of nitride and oxide. If you wanted to draw an equivalent structure for oxide, it would look something like this, where you show, there's a full octet around the oxygen atom, right? The oxygen atom gained 2 electrons, hence a negative 2 charge, and then you have a full octet of 8 electrons in its valence shell. Let's talk specifically about salt formulas that you're going to see. And what I mean by that is, pick something from this side and combine it with something from that side, let's say. For example, potassium sulfide. Why do I have a 2 on the potassium? Well, if I write out everything that is represented in this formula, 2 potassium cations, 1 sulfide anion, what I see here is that the charges have now equal and opposite charges. There's a total of a +2 charge overall from the 2 cations, and that balances out the -2 charge from the sulfide. All ionic compounds do this. For example, if I pick calcium and sulfide to bring together, they're actually going to come together in a 1-to-1 ratio. Why is that? Well, because the +2 charge on the calcium cation balances with the -2 charge on the sulfide in a simple 1-to-1 ratio. You don't need to change the values here. So if they're already opposite and equal, you'll have the 1-to-1 ratio. If they're not, then you're going to adjust the values of the cations and anions so that the charges cancel out. One particular pattern you see over and over again here is that the numerical value on one of these, let's say on the anion, tells you how many of the cations you need. And then the numerical value, in this case 1, for the potassium tells you how many of the anion that you need. And you see this pattern repeating itself over and over again for salt formulas. You can do a similar thing for the polyatomic ions. And for this example, let me go into the transition metals just for a minute. On that previous chart, we saw the iron could be showing up as a +2 or a +3 charge. So now what's going to happen is when either of these cations pair up with phosphide or phosphate, you're going to come up with 2 different salt formulas. So like, for example, if you're presented these 2 formulas, how do you know which one's associated with the +2 and the +3 iron cation? Well, the one thing you have to recognize is that phosphate hasn't changed its charge at all. Phosphate is still, right, PO4 with a -3 charge. This cation, right, you got to recognize that you have the cation on this side and the anion on that side. right? So the anion side has a total of -3 charge. Well, if this is coming together in a 1-to-1 ratio, what did we say earlier? Well, then the charge on the anion and cation are going to be equal and opposite. So that means that this particular example is the one where iron has a +3 charge. So now in this one, iron is going to have the +2 charge. How do we know that? Well, look at the subscripts here. What did we say earlier? Well, this subscript can tell you what the charge is on the cation, and then the subscript associated with the cation can tell you the charge on the anion. And we see that here. These ratios that you see here, again, they are there so that you have equal and opposite charges. If I ink all of this out, I have 3 of the iron 2 cations. If I add up all those charges, that's a +6 total, coming from the cation side of the ledger, if you will. 2 phosphates, add up these charges, it's a -6. Again, all salt formulas are set up so that the ratio of the cation and anion will have equal and opposite charges, so everything's balanced out. Nature likes to be balanced, typically. So again, with this video, I just wanted to do a quick, brief summary of sort of basic ins and outs of salt formulas. I hope it was helpful. Okay, thanks.